All right, if you've ever stared down a tough tree problem in a coding interview, you know that feeling. Well, today we're going to tackle a big one, finding the lowest common ancestor. Seriously, nailing this can be a total game changer. So let's get right into it.
Before we jump into the code and the algorithms, let's just think about this in a really simple way. Picture a huge, sprawling family tree. The lowest common ancestor, or LCA, is really just the closest shared relative between any two people. You know, it's the first person you'd hit if you traced both their family lines up until they finally met. It's the same exact idea for things like file systems, social networks, and of course the data structures we're talking about today.
So, to put it a bit more formally, the LCA of two nodes, let's call them U and V, is the deepest node in the tree that has both of them somewhere down in its branches. And that word deepest, that's the absolute key. We're not looking for just any old common ancestor. We want the one that's as close as possible to the nodes we started with.
So here's our game plan. We're going to break down two really powerful ways to solve this: binary lifting and something called RMQ reduction. Then we'll put them head-to-head to see how they perform, and we'll wrap it all up with a playbook you can take straight into your next interview.
First up is a technique called binary lifting. I like to call this one the jumper. Why? Well, because it's all about making these huge, efficient leaps up the tree to find our answer way faster than just climbing one step at a time.
The whole idea here is to do some work up front, what we call pre-computation. For every single node in the tree, we're going to figure out who its parent is, who its parent's parent is, its fourth ancestor, its eighth, and so on, all the powers of 2. You can just think of these as having magical ladders of different links attached to every node, letting us climb the tree exponentially fast.
Okay, so how does a query actually work with these ladders? It's kind of like a 4-step dance. First, you got to level them up. Take whichever node is deeper and jump it up until it's at the same level as the other one. Now, if they've landed on the same node, hey, you're done. That's the LCA. But if not, we start jumping them both upwards at the same time. And here's the trick. We always use the biggest ladder we can, as long as it doesn't make them land on the same parent. We keep doing that until they're right next to each other, and then bam, their immediate parent is the LCA.
Now, for a second method, which is, well, it's a completely different way of thinking. It's called RMQ reduction. My nickname for this one is the mapper, because instead of jumping around in the tree, we're actually going to flatten the whole thing out into a simple list. And here is where the magic happens. We're going to do something called an Euler tour. Just imagine you're taking a walk around the entire perimeter of the tree. You start at the root and you trace every single edge, both down and back up. Every time you visit a node, and I mean every time, you write down which node it is and how deep it is. This whole process turns our complex tree into one long, simple path. And what's amazing is that the answer to any LCA query is now just hidden somewhere in that path.
And this is where the pure elegance of this approach just shines. To find the LCA of our two nodes, U and V, all we have to do is find the first time they showed up in our tour list. Then, we look at that slice of the list between those two spots and we just find the node with the smallest depth. That's it. That single, shallowest node in that range is, believe it or not, guaranteed to be the lowest common ancestor. It's an incredible transformation of the problem.
Okay, so we've got two really powerful methods here, the jumper and the mapper. So, which one is actually better? Well, like with so many things in computer science, it really boils down to a classic trade-off. How much work you're willing to do upfront versus how blazing fast you need your answers to be.
Let's look at the hard numbers. If we use a cool data structure called a sparse table for our setup, both methods actually take about O and log n time and space to get ready. But here's the kicker, the query time. Binary lifting gives us a very respectable O log n for each query. But the RMQ method? It's O of 1, constant time. That means once that setup is done, finding an LCA is basically instantaneous, no matter how gigantic the tree gets.
So here's the trade-off in plain English. Binary lifting is just, well, it's easier to wrap your head around and definitely simpler to code from scratch. And honestly, its O log n query time is plenty fast for most situations you'll face. The RMQ method, on the other hand, is definitely more complex to set up, but in exchange for that extra brain power, you get those unbeatable, lightning-fast O1 queries, and that can be a lifesaver if you know you're going to be asking a ton of them.
All right, let's bring it all home. You're sitting in the interview, the LCA question gets thrown your way. How do you knock it out of the park? Here's your playbook.
First things first, always clarify the constraints. A great question to ask is this tree static or will it be updated? Next, before you write a single line of code, state the time and space complexity of the solution you're planning. Then, be ready to explain the why behind it all. Why does leveling up the nodes work for binary lifting? Why is the shallowest node in that Euler tour range the right answer? And of course, always mention how you'd handle edge cases.
Okay, you want the golden strategy? Here it is. Start with binary lifting. It's clean, it's correct, and it shows you have a really solid grasp of the fundamentals. Explain its logic, its complexities. Then, if your interviewer pushes you and says, that's great, but can you do better? Can you get those queries down to O of 1? Well, that's your moment to shine. You can then confidently pivot and introduce the RMQ reduction as the more advanced, truly optimal solution. That shows real depth of knowledge.
So, to wrap it all up, the lowest common ancestor problem is a fundamental piece of the puzzle when it comes to trees. And now you know two incredibly powerful ways to solve it: binary lifting and RMQ reduction. One gives you simplicity with great performance, the other gives you unbeatable query speed. The key is understanding the trade-offs and knowing exactly when to pull each one out of your toolkit. That's what separates a good programmer from a great one.
And that leaves us with a really fascinating thought, doesn't it? We just took this complex problem on a tree, and with a really clever change in perspective, we made it solvable in constant time. So the question to chew on is, what other problems out there that seem really hard, or maybe just one clever transformation away from being simple and almost instant to solve?